whether that's true, whether we're simulations or not. That's why I do some things.
Are you also running for president? By the way, Jim Gates is on the President's Commission, Committee of Advisors of Science and Technology, TCAST, and you've been there for almost the entire administration. So keep up the good advice that you're giving. Let's go right here. Hey, how you doing?
Good.
What grade are you in?
8th grade.
8th grade. Cool. So what do you have?
So, you were saying about bugs in the code of the universe if it is a simulation. How come if it probably statistically would not be perfect, how come we have not so far seen any like corruption or glitches maybe looking like the cosmic background radiation? How have we not seen anything that just seems like it couldn't be there?
Great question. Jim, what do you got?
That's an easy one to answer. Up until September of last year, we had never seen gravity waves either. The point is that our technology was not sufficient and might not be sufficient now.
Okay. So what he's saying is that it may still be there, just haven't found it yet. That's a cop-out answer, I think, between you and me, but don't tell him that I said that.
No,
okay. Oh, wait. Yeah, sorry. Yes.
Yeah, so exactly the line of investigation that we had in our paper is whether or not the simulation is imperfect, as you say. So given that we haven't already seen something doesn't mean that we might not see something, and therefore, as I said, we look for evidences that tells us that there are some imperfection in the universe because the simulator or the amount of computation that could be done to generate our universe has been finite. It hasn't been infinite, and therefore there might be some evidence. But it doesn't mean that the fact that we haven't seen it doesn't mean that we shouldn't go and look for it. It's been difficult, but
I thought the question was, why haven't we seen it? That's what I answered.
Well, yeah, and don't you both agree? You're saying if you haven't seen it, doesn't mean it's not there. Absolutely. And keep looking.
Right.
Good. I've got a question from Twitter that came in. Evan Quinter from the Twitterverse asked, I think I'll direct this to Max, if the universe is a simulation, does that mean there's a limit to how far our universe can reach? Because we speak of an infinite universe beyond our horizon all the time. So you're ready to say if it's a simulation, it can't be infinite, and there is the limit to the code.
It's a great question. If we are being simulated in one universe up on finite computational resources, yeah, then either the size of our universe is actually finite, or there's some other trick, like it just keeps repeating itself over and over again.
Like the background in the Flintstones when they're riding in the car?
Precisely.
The background just repeats. I was so angry. I said, you can't draw me. What's with your budget? Ever see the backdrop of cartoons when people are running? It just repeats. When I was a kid, that disturbed me.
Maybe it's a just-in-time simulation. It's kind of like the Truman Show or something. You know, they started off simulating me in Australia, where I was born, and 1 point up. I came to New York, so suddenly they had to simulate all of you guys and
for you.
Yeah, exactly. Or for whoever. Or maybe they start off with the Earth, and then we go to hell. The Voyager just reached the thing just reached Pluto, so I had to simulate Pluto.
I see.
So it's start small, go bigger.
Yeah, don't get me started on Pluto, first of all. But what you're saying is they might be just laying down the bricks in the road as we drive along.
Story of my life, I got no rivals. They all died upon my arrival.
Okay, right here, yes.
Hi. So we briefly discussed infinity and how it relates to this topic, but I was just wondering on the other end of the spectrum,
you ain't nothing but dirt on my shoulders.
Is there not nothing when you come down to the fundamental question?
But we had an entire Asimov panel on that very subject. Where were you?
Yo,
the title of that was called The Existence of Nothing. And we had all the experts on nothing on the stage at the time. I'm just saying. So, okay, maybe he didn't know that.
I actually have a probabilistic argument.
Okay, so we'll entertain it, but go online. The whole thing is there. It's called The Existence of Nothing. Okay, yes.
So in my book, Dark Brown and the Dinosaurs, I have a section on cosmology, and I actually talk about how there is nothing. And I think nothing is just very unlikely. I mean, first of all, we wouldn't talk about nothing if we wouldn't be
Got
here.
him.
But nothing is just one. If you think of a number line, 0 is just 1 point on it. And nothing is just. I was to say
It's
zero
game
is nothing.
time.
And if you have an explanation of why there's nothing, then there's something there that allows you to have the world that explains it.
So you're saying the act of posing the question of why there's something is proof that there could not have been nothing?
Get wrecked.
Right, so there's
Okay,
two
yeah.
I'm
answers.
gonna win.
Crystal clear. No.
That's
Okay.
one answer, and the other answer is probably
Okay, yes, sir. Hi, Dave.
So I think I'm going to do the end program when I wake up in the morning. But the question is, say we assume that we are in a simulation and try to prove it. Would it be possible to come up with equations, knowing what we know from the past, to predict what inputs might be in the future, assuming that it's an original idea
No
and
sweat.
an input from the programmer, and not, on a holodeck within a holodeck within a holodeck? Can you think that would be possible and maybe escape the simulation?
David, what do you have?
Well, I think we're probably stuck for now with the laws of the actual simulation of the simulated universe. If it's a perfect simulation, we're not going to be able to do better than that. We're not going to get information about the character of the simulated universe. Now, if it's a buggy simulation or an interactive simulation, if they're sending messages down here in the way that it's supposed to, and so on, then all bets are off. All I can say is so far, not seeing evidence that we could use to make predictions. Hey, well, tomorrow the simulators are going to, call the whole thing off. So all we can do there is speculate, as far as I can tell. As always, work comes out. Maybe there's something a lot more.
We are living in this universe. We are constrained by the laws of this universe.
Hold
So,
up. Let me figure out which reality I'm in.
Escaping from this universe is logical. We are then evolving according to the laws of this universe, not something beyond that.
Plus, if other universes have slightly different laws of physics, I don't
To all
want to
they
be the
haters
first
who
to
bet
visit
against
them.
me, y'all keep hating. That don't
Send
offend
something
me.
else, then we'll figure it out. We only have time for a couple more questions, one of which I'm going to take from our Twitter list. But let's go right here, sir. Yes.
Sorry, no, I tend to disagree with your conclusion about the universe simulation percentage and more agree with Lisa's 0%.
This will be over real quick.
Using the chessboard analogy, yes, there's 64 pieces on a chessboard. You can assign numbers to each piece.
There's 64
The
squares.
64 squares, right. And each you can assign values, numerical values to the chess pieces, and then use computers to see if the number applies, 3, 4, 5, and then run the simulation, and you get the end result, see who's going to win, and so forth. However, just look at
This is how I do.
humans on this earth. We have 7 billion people now on Earth, and even we can mathematically model one person. When you have interactions of each other, we have interactions of more than each other, because every action there's a reaction, and then we have 7 billion people. So the result is going to be totally unpredictable. In fact, it doesn't look too good because, the Earth with its limited resources, this whole population growing, at a logarithmic, rate.
Exponential rate.
Conclusion.
Yeah.
So
Son,
then
really check your style. I'm gonna lie to them.
one conclusion
Stay
that is,
fresh.
the result is not good. So.
But it may be that these multiple interactions that transcend our native ability to
Been a
compute
minute since I took a
are no
L.
different from the tic-tac-toe game being played by the 5-year-old,
Don't pray for me, pray for my
which is
enemies.
too stupid to know.
Well, that's true.
That's right.
But again, when you look at the complexity and try to mathematically model 7 billion people's characteristics.
Yeah, we can't
very
do it
difficult.
because we just have human
Absolutely.
brains.
Thank you very much.
Yeah, sure. Forgive the rest of the people online. The last question is going to have to be from
This is for my
our Twitter
city.
stream here. And this one I'm going to send to Lisa. Lisa, you will take us out with your answer to this question. This is from Ashley Camino. Is dark matter, with multiple ways to how it's different, but let me say it as it's written. Is dark matter transparent or simply rules of the game, a computational structure, like an operating system. And think of dark matter and dark energy, these permeating elements of the universe that we don't understand at all. We don't know what's causing them, but we can measure their existence. Could that be the blood of the operating system throughout the universe?
So it's an interesting question, and people have asked that question. And you have to take a little bit of an Occam's approach here. So first of all, dark matter is indeed transparent matter. It's matter that just light just goes through. There's evidence for it not because you see it, because it doesn't emit or absorb light, but because it has gravitational influence, and you can observe the gravitational influence. Now you can ask, is that because we got the law of physics wrong and there really wasn't matter and we got the law of physics wrong? Now, first of all, it's a lot simpler to believe this matter that we have no reason to believe shouldn't be there is there than to think we got the laws of physics wrong. Because the laws of physics work incredibly well over many different scales, so there's no evidence that those laws of physics are wrong.
Hang tight.
But furthermore, there's more and more evidence that makes it look just like it's matter. One of the things is known as the bullet cluster or other clusters, which are really mergers of clusters of galaxies.
But my music about to change
Clusters of galaxies are bound states of many galaxies head together. And when those things go through each other, a cluster of galaxies has gas in it, it has stars, and it has dark matter. What goes through it, you see the gas gets stuck in the middle. You can see that through X-rays. Through gravitational motion, you can see the dark matter just pass through it. It acts just like you would expect matter that's not interacting to act. It goes right through, the gas stays in the middle. Now you can try to mock up equations or some simulation or something that does that, but it looks just like matter does. It's exactly what you would predict.
Except we established earlier that we don't form our own galaxies without the existence of dark matter creating the womb in which we collapse. So is that kind of like an operating system, enabling matter to do its thing?
Well, gravity is, in some sense, the operating system. But gravity is responding to the existence of the dark matter. And dark matter does play a big role. There's more of it. It collapses. It doesn't interact with light, so it can form structures more easily than normal matter.
I like that. Gravity is the operating system. Well, how about dark energy?
Dark energy is another just
My head's held high, but my feet are on the ground.
to gravity. So dark energy is, for those who don't know, it's smoothly distributed. It's not like matter. It's not the operating system either.
The operating system is everywhere you touch on a computer. So is dark energy.
I'm just getting confused now. It's part of what I put in, at least in my initial
better watch out for my comeback.
state, and then I let the gravity equations work on it. So you have this distribution of energy, you have this distribution of matter, and then you can ask, what is the effect of this energy that we don't observe directly? In some sense, we observe the fact that it is responsible for the acceleration of the expansion of the universe. But gravity is the only law.
Echoes the
there.
name, the
The
crowds
other stuff is
acclaim.
just stuff.
Didn't act for
Dark
fame, I
energy is
changed the
stuff.
game.
Dark matter is stuff. The gravitational equations are acting on that, and it's actually creating the gravitational force.
Well, so if gravity is the operating system of the universe, I can't wait for Universe 2.0. Thank you all for coming this evening. And thank the panel. Zore, Max, Jim, Lisa, David.
Always so much fun.
Thanks for coming out. That concludes the 17th annual Isaac Asimov panel debate. Good night to you all here in New York. We'll see you next year.
Here I go.
Hey everyone, it is that time of the week again for our live conversation where, as part of your daily equation, I'm happy to cover anything that is equation related, and of course these equations are related to everything. That means everything is game. So truly feel free to ask me about anything that's on your mind. You know me, if I don't know the answer, I'm straightforward, I tell you. If I have something to say on the subject, I'm happy to offer it. And let's begin, as we sometimes do, and I see Luis has already noted that he is in our conversation from Mexico, but I do like to see the various places where everybody is from. So if you don't mind just sort of saying where you're from, I would love to see that. And then as
I'd rather
those
be myself than
countries
please anyone
roll
else.
by, I will be all too happy to start finding the first questions and get moving on things.
Heads up!
All right, so what do we have here? What am I going to begin with? There was one question I really wanted to begin with, and I didn't have a chance on YouTube to locate who it was that asked it. But somebody asked in one of the last two sessions about what it means when people say that time is curved. Right, in the general theory of relativity and special relativity too, of course, we know that space and time are all together. They're blended into this uniform continuum that we call space-time. So if we learn that space is curved in the general theory of relativity, then we must know that time is curved too. But you know, we all have an image for what curved space is, but what does curved time mean? And the answer to that is less mysterious than it sounds. It's not like you have a Dali-esque like clock that sort of warps time in some literal spatial way. Of course, a clock is warped in space. It's not itself warped in time. But when we say that time is warped, we simply mean that the rate at which time passes at different locations need not be the same. And in particular, what we learn in the general theory of relativity is that if you have a massive body that exerts the force of gravity or curves the environment around it, the space-time environment, what that means is the closer you get to that body, the slower clock gets. So if you had a clock, say, that is at the top of the Empire State Building, you have another clock on the ground floor there at 34th and 5th Avenue, whatever the right address is, I think that's correct. Then the clock at the top of the Empire State Building will tick off time a little more quickly than the clock at the bottom of the Empire State Building. So time is warped in that sense. You know, if you have a ruler that's warped, then different parts of the ruler will measure different distances between the same two locations, right? That's what a warped, non-uniform ruler would do. If you have time that's warped, then clocks will not measure the same elapsed time between two events
I got no one inspired.
by virtue of this warped or curved nature of time. Now, for the example of the Empire State Building, you say, well, why don't I know about that? The reason, of course, you all absolutely already know as well. The amount of time warpage, time curvature between the top and the bottom of the Empire State Building is tiny, tiny fraction of a second. You just don't notice it. But if you took that same example and you put the Empire State Building at the edge of a black hole, then the clock near the edge of the black hole, closer to the source of gravity, would tick off time far more slowly than the clock farther away. And that would, in principle, be a measurable time difference. Right? I think as mentioned before, in Interstellar, you saw that example directly, like the astronauts that went down to the planet that was closer to the black hole than the crew member who stayed up in the ship. They just spent a couple hours in that environment, but time is ticking off so slowly for them, so quickly, compared to the clock on the mothership, that when they returned to the ship, their fellow crew member had aged like 20 years, where they had only aged a couple of hours. So that's what we mean by curved time. All right, moving onward. What else do we have here? So Salim Yagi says, Dr. Green, thank you for amazing words. Is it scientifically correct to say that gravity is due to a field property of space-time, or is it just pure objective geometric property of space-time? And it's a very good question, because we physicists freely go back and forth between the language of a gravitational field and the language of the geometry of space-time. And I would encourage you to feel comfortable going back and forth between those languages as well. In fact, you should feel comfortable using the standard Newtonian language as well, where you talk about a force of gravity, one object pulling on another. Because depending on the problem at hand, one or another language can give you the greatest insight. Einstein's general theory of relativity language is indeed one in which we think about gravity as nothing but the curvature of space-time. So why do objects move in interesting trajectories under the old Newtonian language of the force of gravity? Einstein's answer: they move in these interesting trajectories, these orbits, because they are sliding along these grooves, these indentations, these valleys in the geometrical structure of space-time. So there's a sentence where I use the Newtonian gravitational force language, which is also the Newtonian gravitational field language, and also the Einsteinian geometrical language for the shape of space-time. And so freely move in between those languages as befits whatever situation you are in. Now let me just give one example, and I'm gonna, in your daily equation of next week, boy, it is really windy here. I don't know if you guys can hear this, but in a moment I may need to close down the windows, even though it's quite hot in here. But next week in your daily equation, I'll make this point as well.
Nothing I can't do.
In the Newtonian description, right, the apocryphal or perhaps real story has it that this apple fell from the tree and it hit Newton in the head. And the Einsteinian description in terms of the geometry of space-time is actually quite different, because the freely falling objects in Einstein's view, they are the ones that set the standard of rest. And therefore, in an Einsteinian description, the apple, when it's in free fall after it detaches from the branch, it's just sort of hovering there in space-time. And it's Newton's head that comes up and slams into the apple, because Newton is not in a freely falling frame sitting on the surface of the Earth. The Earth's surface is getting in the way of Newton's free fall. Newton can't fall through the rock of the surface of the Earth, even though his body would like to. So that actually helps us understand the ancient puzzle that you all know the answer to, but why is it that two different objects fall at the same rate regardless of their mass? I could try to do this, but I'll make a mess of it, so I better not. But you know what I mean. You take two objects. I don't want to break the Apple Pencil, then I won't be able to do your daily equation. But I let them go, and they both fall together. Why is that? According to Newton, it's because there's equality between gravitational mass and inertial mass, which means they both cancel out of the F equals ma equation when the force is equal to mm over r squared times g. That's equal to m times a. The m's on both sides cancel, so it's only the big mass of the Earth that really determines the acceleration of each of these objects. Therefore, they fall together, but that's a mystery. Why is gravitational mass equal to inertial mass? Einstein's answer is completely different. Einstein says, when you let go of these two objects, I'm not going to do it again, but when you let go of them, they're in free fall from your perspective, which Einstein says sets the standard of rest. Now imagine, therefore, that they are at rest in space-time, and it's the Earth that's rushing up to them. So why do they hit the Earth at the same moment? Einstein's answer is very straightforward. They hit the Earth at the same moment because they don't move. It's just the Earth that comes up and meets them, and the Earth has a singular body. When it moves up to their location, it hits them, and of course it hits them at the same moment. They were just sitting there waiting for the Earth's arrival. So that's the geometrical Einsteinian view, and in that case it does give us insight that otherwise would be hard to glean. Okay, so what else do we have? Alina says, big fan of your videos. Thank you, Alina, I appreciate that. Abu Bakar Faruqi. Greetings, Professor Green, watching you from Pakistan. Wow, that's great to hear. What is your view regarding the idea that the entire universe is inside a black hole? Well, it's an interesting question. First of all, talking about the entire universe inside a black hole is a bit extreme, but what I would say is, it is possible that, at least according to the traditional general relativistic description of black holes, I'm not going to modify it with modern or more recent conjecture, speculations about firewalls and all that sort of good stuff. So let's just act as though Einstein had the important word on black holes. But if that's true, then right now, it's quite conceivable that the Earth just passed across the edge of a black hole, that we are all now inside of a black hole. Why is that? The edge of a black hole, in Einstein's description, is not some special location in space. It's just an ordinary chunk of space that has the unusual property that once you pass that location, the event horizon, you are no longer able to get out. But you don't have any direct physical reaction to crossing over the event horizon of a black hole. And so right now, everything, as we look around the world, we could all be within a black hole, and we'll only really recognize that later on when we get closer and closer to the center of the black hole, because then, depending on our precise distance from the black hole, different parts of the Earth, different parts of our body will feel a different force. If we're going feet first toward the center of the black hole, our feet will experience a greater pull than our head. Our body will be stretched. Spaghettified is the technical term that we use for this process, until ultimately we're pulled apart into our constituent particles that will all rain down on the singularity, whatever that is, the center of the black hole. We don't really understand what goes on there. So in that sense, we could all be within a black hole right now. I'm not exactly sure how to describe that if you want to truly think of the entire universe, but any large chunk of the universe could follow exactly the same process that I just described for the Earth, and therefore, in that sense, we could be within a black hole. Nikhil Pahalani says, hello, Professor Green, I'm a computer science student in India. Boy, a lot of Pakistan, India today. That's fantastic. Recently developed interest in physics because of you. Oh, that's great to hear. It really is great to hear. It's so inspiring to hear that these little videos that I created, you actually reach out. So thank you for telling me about that. The question is, can you guide me if I can do both together, namely computer science and physics, and where I should start? And the answer is absolutely. Number one, the distinctions between computer science and physics have certainly been blurred in the last few years in a substantial way, because one of the dominant, interesting problems that people who have been focusing their attention on quantum mechanics for a long time, that they're focusing on is quantum computing. To really see whether we can inject our understanding of quantum physics into a new kind of computational procedure. Now look, of course, every computer in some sense is a quantum computer, because the integrated circuit only exists because we can manipulate the motion of tiny particles like electrons, and we need quantum mechanics to understand how to do that. But quantum computing takes that into a radically different direction, not just the technological innards of a computer to be governed by quantum physics, but rather the computational process itself, making use of the full might, the full power of quantum mechanics. Roughly speaking, if you buy into the many worlds interpretation of quantum mechanics, it's as if we're trying to build computers that will do parallel processing of certain kinds of computational procedures across the many universes that quantum reality spans, make use of all of those universes to simultaneously crack apart various parts of an interesting calculation and find a manner of pulling out the solutions that we are looking for from this broad swath of parallel computational procedures. So I don't know if that kind of blending of physics and computer science fires you up, Nikhil, but that certainly is an arena in which you would be well posed to make a contribution by carrying on with your studies in computer science, but also building up your understanding of physics with all the standard things, classical mechanics, quantum mechanics, thermodynamics. You need all of that, and some of that you can learn on your own. So I would look at, wherever you are, the course of study that's available to see about blending these, but it's not as though you're saying to me, I want to dance in the Bolshoi ballet, and I also want to be the next Einstein. not impossible. And I would actually encourage you if that was your dream. But what you're saying is more easily attainable than that particular goal, that particular dream, because computer science and physics are no longer as far apart as perhaps your studies might suggest that they are. Okay, what else do we have? There's an interesting question here. Oh, here's one from China. Yuping Zhang. Hi, Professor. Big fan from China. Thank you, Yuping. If I move close to the speed of light relative to you, but from my perspective, you are the one who is moving fast. So in the end, who is getting older? And yeah, Yuping, that is a puzzle. It is one that people have kicked around for a long time. We think we understand it quite well, which is that the notion of who is getting older is a question that needs to be framed with greater precision in order to really answer your question. And the real question is, if you and I get back together and we compare our ages either visibly or more precisely with our watches, on whose watch will more time have elapsed? And if it's the case that I, say, am not experiencing any, say, acceleration during this entire journey, right? This entire journey, I'm just sort of sitting around and I never feel a force on my body. I never feel a change in my speed. But you, in order to come back to me, must feel that change. Let's say you go out in space, you've got to turn around and come back. That turnaround is an acceleration. You will feel it. It is a change in your velocity, a change in the speed and direction of your motion. And that's what breaks the symmetry that otherwise would be quite confusing. And because of that break in symmetry, you feel the acceleration, but I do not, then it turns out that you can establish that you are the one that is going to be younger on the return. I will be the one who is older.